Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today, we are going to discuss about the module Waveguides and Cavities from the paper Electromagnetic Theory. From this module, you will get to know about the following. Firstly, you will get to know about the boundary conditions that need to be satisfied in and around a perfect conductor. Then you learn about the use of hollow metallic structures for guided propagation of electromagnetic waves. Then you will also learn about the various modes of propagation in waveguides, the transverse electric mode, the transverse magnetic mode, and the existence of cutoff frequencies. Then we'll do a detailed study of the rectangular waveguides for the two types of modes, that is the TE and the TM modes. And then we'll also study the cavity as a resonator, existence of the resonant frequencies inside a cavity. And finally, we'll do a detailed study of the cylindrical cavity resonator and selection of the fundamental resonant frequencies and tuning. So far, in the study of electromagnetic waves, we have discussed waves of infinite extent without any boundaries. We now wish to study waves confined in hollow spaces, that is, the interior of hollow pipe. Study of such systems is of considerable practical importance. The only practical way of generating electromagnetic waves for wavelengths in the region of a few meters is through such metallic structures of size of the order of the wavelength. If the hollow pipe has end surfaces, it is called a cavity. If not, it is called a waveguide. We will first study fields in and outside of perfect conductors. Next, we will study the propagation of waves in waveguides and in cavities. We will ignore complications due to finite conductivity, which lead to attenuation of waves in guides and broadening of the resonance in cavities. Waveguides and cavities. We wish to study the waves confined in hollow spaces, that is, the interior of a hollow pipe. Study of such systems is of considerable practical importance and provides the only practical way of generating electromagnetic waves for wavelengths in the region of a few meters. If the hollow pipe has end surfaces, it is called a cavity, otherwise a waveguide. So let us assume that the guide is a perfect conductor of general cylindrical shape. Assume the sinusoidal dependence, that is e to the power minus I omega t, such that the partial time derivative would yield del by del t will lead to minus iota times omega. Then the Maxwell's equations for such a system will take the form: the divergence of the electric field is zero. That means that there are no sources, charge sources in the said system. The curl of the electric field is equal to iota times omega times the magnetic field induction vector B. The divergence of the magnetic field is equal to 0, and the curl of the magnetic field is equal to minus iota times mu times epsilon times omega times the electric field vector E, where epsilon is the electrical permittivity of the medium and mu is the magnetic permeability of the non-dissipative medium filling the cylinder. Take the curl of either of the curl equations and one can then obtain the following equations: waveguides and cavities. Now, combining the four of Maxwell's equations for the case of waveguides and cavities, that is, for case where we have a hollow cylindrical waveguide or cavity where the hollow part is having a dielectric medium or maybe free space, while the cylindrical part is basically a conducting metallic waveguide or a cavity. So for such a situation, we can combine the Maxwell's equations to give two equations, that is the homogeneous equations in the Maxwell's equations can be combined into one equation and can be rewritten as del square plus mu times epsilon times omega square whole within brackets times the magnetic field induction vector B is equal to 0. So we get these two wave equations for the waveguides and cavities, and when we take the axis of the symmetry of the tube to be along the z axis and separate out the z dependence of the fields and operators, then we can rewrite the electric field as electric field vector is given as vector E as a function of the position vector x and time t is equal to vector E as a function of the x coordinate and y coordinate whole times e to the power I bracket open plus minus k times z minus omega t bracket close. The magnetic field induction vector B as a function of position vector x and time t is equal to the magnetic field induction vector B as a function of coordinate x and coordinate y times e to the power I plus minus k times z minus omega t. The del operator can also be written in terms of the z component and the transverse component, given as the del operator del vector is equal to del vector subscript t plus unit vector z times del by del z, where del vector subscript t denotes the transverse component or the component lying in the xy plane. So, and similarly, the del square operator can then be written as equal to del square transpose plus del 2 by del z2. And using these definitions and the way we have separated out the transverse component from the longitudinal component, we can rewrite the above equation as the del square transpose plus within brackets mu times epsilon times omega square minus k square bracket close whole within brackets times the electric field vector is equal to 0, and similarly bracket open del square transpose plus within brackets mu times epsilon times omega square minus k square bracket close whole bracket close times the magnetic field induction vector B is equal to 0. Since these are equations have the wave equation form, therefore we can take an appropriate combination of the two waves and we can write the time dependent part as e to the power I bracket open plus minus kz minus omega t bracket close, and obtain either a traveling wave or a standing wave depending upon the situation and the various other parameters or restrictions. Now, unlike free space, the field inside a hollow tube can have longitudinal components as well as transverse components. So it is important that we separate the field into these two different types of component, that is the longitudinal component which is along the z-axis and the transverse components. Waveguides and cavities. Now separating out the longitudinal, that is the component along the z-axis, and the transverse, that is the components in the xy plane for both the electric field and the magnetic field, we can write down these components as, so the electric field is equal to the electric field transpose plus the electric field along the z-axis given by Ez, where the Ez vector is equal to Ez times unit vector z, and the E transpose vector is equal to E vector minus Ez vector, and this is equal to unit vector z cross product with the electric field whole cross product with the unit vector z. So that's a vector triple product. Similarly, the vector magnetic field vector induction vector B is equal to the transverse component of the magnetic field induction vector B plus the z component of the magnetic field induction vector B, where the z component of the magnetic field induction vector is equal to the z component of the magnetic field induction with times the unit vector z, while the transverse component of the magnetic field induction vector is equal to the magnetic field induction vector B minus the vector along magnetic field induction vector B along the z-axis, and this is given as bracket open the cross product of the unit vector z with the magnetic field induction vector B bracket close whole cross product with the unit vector z. So using all these different components that we have decomposed these fields into, we can then write down the Maxwell's equations and get the following equations, which are the partial derivative of the transverse component of the electric field with respect to z plus iota times omega times unit vector z cross product with the transverse component of the magnetic field induction vector B is equal to the transverse component of the del operator acting on the z component of the electric field. Similarly, the dot product of the unit vector z with the curl of the transverse del operator and the transverse component of the electric field vector is equal to iota times omega times the z component of the magnetic field induction B. The other set of equations that we get are the partial derivative of the transverse component of the magnetic field induction vector B with respect to z minus iota times mu times epsilon times omega times the cross product of the unit vector z with the transverse component of the electric field vector E is equal to the transverse component of the del operator acting on the z component of the magnetic field induction, and the dot product of the unit vector z with the cross product of the transverse component of the del operator and the transverse component of the magnetic field induction vector B, and this is equal to minus iota times mu times epsilon times omega times the z component of the electric field. Then the divergence of the transverse component of the del operator and the transverse component of the electric field is equal to minus of partial derivative of the z component of the electric field with respect to z axis and the divergence of the transverse component of the del operator with the magnetic field induction vector B transverse component is equal to minus of partial derivative with respect to z of the z component of the magnetic field induction. So if the z components of the fields are known, the transverse components can be obtained from the following relations. So using these above equations that we have defined, we can write down the transverse component of the electric field vector is equal to iota upon mu times epsilon times omega square minus k square whole times bracket open k times transverse component of the del operator acting on the z component of the electric field minus omega times unit vector z cross product with the transverse component of the del operator acting on the z component of the magnetic field induction Bz. Similarly, the transverse component of the magnetic field induction vector B transverse is equal to iota upon mu times epsilon times omega square minus k square whole times bracket open k times the transverse component of the del operator acting on the z component of B plus mu times epsilon times omega times the cross product of the unit vector z with the transverse component of the del operator acting on the z component of the electric field Ez. The transverse magnetic and transverse electric modes. Now once we have defined the electric field and the magnetic field in terms of their transverse and longitudinal components, where the longitudinal component is along the z-axis, and further we have defined the transverse components of the electric field and the magnetic field induction vector in terms of their z components, we can now move on to defining what is the transverse electric and the transverse magnetic fields. So in case of transverse electric fields, we put the longitudinal component of the electric field going to 0, that is Ez goes to 0, and these are called the transverse electric waves. Similarly, if the longitudinal component of the magnetic field induction vector, that is Bz, goes to 0, then the corresponding waves are termed as the transverse magnetic waves. While if the transverse component of the electric field as well as the magnetic field induction vector both go to 0, that is Ez also goes to 0 and Bz also goes to 0, then we have the transverse electric magnetic waves or the TEM waves. However, in case of a hollow waveguide or cavity, we cannot have the transverse electric and magnetic waves existing. That is, the TEM waves cannot exist inside a hollow waveguide or cavity. For TEM mode to exist, it is necessary that we have two or more cylindrical surfaces. Now let us look at the transverse magnetic and the transverse electric modes, that is the TM and the TE modes. Now looking at the boundary conditions at the boundary of the perfect conductor with the dielectric interface or the dielectric medium, we know that at the boundary, the tangential component of the electric field should go to 0, while the normal component of the magnetic field should go to 0. That is, at the interface of the conductor and the dielectric, both the tangential component and of the electric field as well as the normal component of the magnetic field are continuous. This condition basically gives us that the cross product of the normal unit vector with the electric field is equal to 0, while the dot product of the normal unit vector with the magnetic field induction vector is equal to 0. So from this we can see that the partial differential equations or the wave equations that we had defined earlier for the fields together with the corresponding boundary conditions that we have defined above leads to an eigenvalue problem for the fields. Also, that for a given frequency, only certain specified values of the wave number k are allowed. Further, for any cavity, this becomes an eigenvalue problem in the frequency, which is something that we are going to be studying slightly later. And that the boundary conditions for the transverse magnetic and the transverse electric modes are different, then the eigenvalues are also in general different. Waveguides. So taking all these conditions into account, we then say that the fields can thus be divided into two classes. One, the transverse electric or the TE waves, in which case the Z component of the electric field Ez is equal to 0, while the partial derivative of the Z component of the magnetic field induction Bz with respect to the normal unit vector del Bz by del n at the surface of the metal or the conductor with the dielectric is also equal to 0. Similarly, the other condition that we define is that of the transverse magnetic waves or the TM waves, where the Z component of the magnetic field is 0 at the interface, that is Bz at S is equal to 0, while the partial derivative of the longitudinal component of the electric field, that is del Ez by del n, is equal to 0 at the surface. Now let us look at the waveguides. So let us take the Z dependence of the form e to the power iota times k times z. Then del by del z can then be represented or replaced by iota times k. So using the equations that we had defined above for the transverse components of the electric field and magnetic field, that is, right, when we had written down the Maxwell's equations in terms of the transverse and the longitudinal components of the electric and the magnetic fields. So using those equations and the relation between the transverse fields, both for the transverse magnetic and the transverse electric modes, waveguides. So taking all these conditions into account, we then say that the fields can thus be divided into two classes. One, the transverse electric or the TE waves, in which case the Z component of the electric field Ez is equal to 0, while the partial derivative of the Z component of the magnetic field induction Bz with respect to the normal unit vector del Bz by del n at the surface of the metal or the conductor with the dielectric is also equal to 0. Similarly, the other condition that we define is that of the transverse magnetic waves or the TM waves where the Z component of the magnetic field is 0 at the interface, that is Bz at S is equal to 0, while the partial derivative of the longitudinal component of the electric field, that is del Ez by del N, is equal to 0 at the surface. Now let us look at the waveguides. So let us take the Z dependence of the form e to the power iota times k times Z. Then del by del Z can then be represented or replaced by iota times k. So using the equations that we had defined above for the transverse components of the electric field and magnetic field, that is, right, when we had written down the Maxwell's equations in terms of the transverse and the longitudinal components of the electric and the magnetic fields. So using those equations and the relation between the transverse fields, both for the transverse magnetic and the transverse electric modes, we can write down the transverse component of the magnetic field is equal to the transverse component of the magnetic field induction vector by mu, and this is equal to 1 upon Z whole times unit vector Z cross product with the transverse component of the electric field, where Z is equal to k upon epsilon omega, and this is equal to k by k naught times under root of mu by epsilon for the transverse magnetic mode, where k naught is given by omega times under root of mu epsilon, and capital Z is equal to mu times omega upon k is equal to k naught upon k times under root of mu by epsilon. This is for the transverse electric mode. Here again k naught is equal to omega times under root of mu epsilon. So the general equation that needs to be solved is the two-dimensional wave equation given by bracket open del transpose square, that is the transverse component of the del operator whole square, plus capital K square bracket close acting on the wave function psi is equal to 0, along with the conditions that in case of transverse magnetic modes, the wave function psi at the surface is equal to 0, and in case of transverse electric modes, the partial derivative of the wave function with respect to the unit normal, that is del psi by del N at the surface, is equal to 0. Waveguides. So using this general formulation for the wave equation both for the transverse magnetic and the transverse electric modes in 2 dimensions, and using the equation that define the transverse component of the electric field and the transverse component of the magnetic field, we then can write down that the wave equation for the transverse electric waves is given as the transverse component of the magnetic field induction vector H transverse is equal to iota times k by capital K square whole times the transverse component of the del operator acting on the wave function psi. And for the transverse magnetic waves, it is given as the transverse component of the electric field is equal to iota times k by capital K square whole times the transverse component of the del operator acting on the wave function psi, where capital K square is equal to mu times epsilon times omega square minus k square. And in order to satisfy the boundary conditions on the opposite sides of the cylindrical surface, the wave function psi must be oscillatory, which means that the capital K square that we have defined above must be positive. This leads to a set of eigenvalues and corresponding eigenvectors, which are denoted by capital K subscript lambda square and psi lambda subscript lambda, where lambda is equal to 1, 2, 3 and so on. And these are the various modes of the waveguides. So for a given frequency, there is a corresponding wave number, which can be written as small k subscript lambda square is equal to mu times epsilon times omega square minus capital K subscript lambda square, follows that small k subscript lambda is equal to under root of mu epsilon whole times under root of omega square minus omega subscript lambda c square, where omega subscript lambda c is equal to capital K subscript lambda by under root mu epsilon, and this is called the cutoff frequency corresponding to the particular mode having wavelength lambda. Waveguides. For omega greater than omega subscript lambda ski, the wave number is real. Waves of this mode can propagate in the waveguide. For omega less than omega subscript lambda c, the wave number is imaginary. Such waves cannot propagate in the guide. These modes are called the cutoff or the evanescent modes. As frequency increases, it becomes higher than the cutoff frequency for more and more values of the wavelength lambda. However, for any given frequency, only a finite number of modes can propagate. The eigenfrequencies depend on the dimensions of the waveguide. The dimensions are often so chosen that at the operating frequency, only the lowest modes can propagate. Inside a waveguide, the wave number is always less than its infinite space value. That is, the wave number k is equal to under root of mu times epsilon whole times omega. Hence, phase velocity is always greater than the infinite space value. However, group velocity is always less than its infinite space value. Rectangular waveguide. Modes in a rectangular waveguide. Now let us look at the case of transverse electric waves in the rectangular waveguide. So considering the Cartesian coordinates, the wave equation for the transverse electric wave takes the form bracket open del 2 by del x2 plus del 2 by del y2 plus capital K square bracket close whole acting on the wave function psi as a function of x and y is equal to 0, with the boundary condition that the partial derivative of the wave function with respect to the unit normal, that is del psi by del n, is equal to 0 at x equal to 0 and x equal to L, and at y equal to 0 and y equal to b, where x equal to 0 and x equal to L define the boundary conditions of the x-axis, and y equal to 0 and y equal to b define the boundary condition of the y-axis. So applying the usual method of separation of variables, we then obtain the relation for the wave function psi given by psi subscript m(n) as a function of coordinates x and y is equal to h naught times cos of m pi x by L times cos of n pi y by h, where m and n are integers which take the value 0, 1, 2, 3 and so on, and m and n are not equal to 0. So substituting this value of psi subscript mn, where mn denotes the mode of the transverse electric wave, we get the differential equation as capital K square subscript mn is equal to pi square times bracket open m square by L square plus n square by h square bracket close. Rectangular waveguides. Now, after having found out the relation for capital K square subscript mn, we can then write down the relation for the cutoff frequency for various modes given by omega subscript mnc is equal to capital K subscript mn upon under root of mu epsilon, and this is equal to pi by under root of mu epsilon whole times under root of bracket open m square by L square plus n square by h square bracket close. So if L is greater than h, then the lowest frequency mode that can occur for a rectangular waveguide is given for m is equal to 1 and n is equal to 0. This is the dominant transverse electric mode, and the cutoff frequency and the explicit fields for this transverse electric 1,0 mode are then given by omega 10 c that is the cutoff frequency for the 1-0 mode, is equal to pi by under root mu epsilon whole times 1 by L. This is the equation that we can obtain by substituting the value of m equal to 1 and n equal to 0 in the above equation for omega subscript m and c. And the value of the wave number k comes out to be k is equal to under root mu epsilon times under root of omega square minus omega subscript 10c whole square. So the value of the longitudinal component of the magnetic field then turns out to be hz is equal to h naught times cos of pi x by L times e to the power I bracket open kz minus omega t bracket close. The x component of the magnetic field is given as hx is equal to minus iota times k times L times by pi whole times h naught times sine of pi x by L within brackets e to the power iota times kz minus omega t. Since we are considering transverse electric modes in the rectangular waveguide, therefore the longitudinal or the z component of the electric field is equal to 0, while the y component of the electric field Ey is equal to iota times mu times omega times L by pi whole times h naught times sine of pi x by L e to the power I bracket open kz minus omega t bracket close. For the transverse magnetic mode, the field will be given in terms of sine functions. And the lowest cutoff frequency in case of the transverse magnetic modes for a rectangular waveguide will then correspond to m is equal to n is equal to 1, that is TM11 mode will be the mode permissible with the lowest cutoff frequency. Hence, we see that the TE10 mode has the lowest cutoff frequency amongst all modes that are permissible in the rectangular waveguides, and the ratio of the lowest cutoff frequency with that of any other cutoff frequency. Then what we have to consider is the ratio of the dimensions L by H. So if we consider the case where L is equal to twice of H, then the value of the lowest cutoff frequency omega subscript m and c is equal to pi by under root mu epsilon whole times under root of bracket open m square by L square plus 4 n square by L square bracket close, and this is equal to omega subscript m and c by omega 1 subscript 10c is equal to under root of m square plus 4 n square. And for this example, one sees that the frequency range omega subscript 10c is less than omega is less than twice of omega subscript 10c, where omega 10c denotes the lowest cutoff frequency of the transverse electric 10 mode, and in this range only the TE10 mode can propagate. Now let us consider the case of resonant cavities. So again, we define a cavity with a cylindrical shape and arbitrary shaped cross section having length L with the axis of the cylindrical cavity along the z direction, closed by planar surfaces normal to the axis and filled with a dielectric medium having dielectric constant A or the electric permittivity epsilon and the magnetic permeability mu. So the waves in the cavity enclosed by planar surfaces at the two ends. So the waves inside such a cavity will be standing waves along the z direction, and the wave equation for such standing waves can then be written as psi is equal to A1 times sine of kz plus A2 times cos of kz, and the resulting eigenvalue problem will have the solution given by k is equal to j times pi by L, where j is equal to 0, 1, 2 and so on. Here we substituted the wave function psi in the above wave equation that we had derived for the waveguides. So now applying the boundary condition for the transverse electric mode, that the longitudinal component of magnetic field Hz is equal to 0 at Z is equal to 0 and Z is equal to L, that is at the beginning and the end of the cylindrical resonant cavity. We can then write the Z component of the magnetic field as given by psi as a function of x and y times sine of j pi z by L, where j is equal to 1, 2, 3 and so on is an integer. Resonant cavities. Similarly, if we want to write down the boundary conditions for the transverse magnetic mode, then we can write down that the derivative of the z component of the electric field with respect to z coordinate is equal to 0 at the boundary, that is at z is equal to 0 and z is equal to L. And from this, the z component of the electric field can be written as psi as a function of xy times cos of j pi z by L, where j is an integer taking values 0, 1, 2, 3 and so on. So finally, we can write down the transverse electric mode for the resonant cavity as given by the transverse component of the electric field is given by minus iota times omega mu by capital K square times sine of j pi z by L times unit vector z cross product with the transverse component of the del operator acting on the wave function psi, and the transverse component of the magnetic field is vector is given as j times pi upon L times capital K square whole times cos of j pi z by L times the transverse component of the del operator acting on the wave function psi. For the transverse magnetic mode, we get the transverse component of the electric field as given by minus j times pi by L times capital K square whole times sine of j pi z by L times the transverse component of the del operator acting on the wave function psi, and the transverse component of the magnetic field vector H transverse is equal to iota times epsilon omega by capital K square whole times cos of j pi z by L times the unit vector z cross product with the transverse component of the del operator acting on the wave function psi. Solving these equations, the eigenvalue problem for the differential equation with the wave number k equal to j times pi by L yields the value of capital K square is equal to mu times epsilon times omega square minus within brackets j pi by L whole square, and from this we can then find out the value of the angular frequency omega subscript lambda j is equal to 1 upon under root mu epsilon whole times bracket open capital K square subscript lambda plus within brackets j pi by L whole square bracket close whole to the power half, and the resonant frequencies can then be found out with the value of the wave number k is equal to j pi by L. Cylindrical resonant cavity. Now let us consider the case of a cylindrical resonant cavity which has a radius of the cavity as r and the length of the cavity as L. So the differential equation in cylindrical coordinates has the solution. We now define the wave function in terms of the cylindrical coordinates. So wave function psi as a function of rho and phi is equal to capital J m times within brackets capital K m n times rho whole times e to the power plus minus I m phi. The transverse magnetic mode can now be defined for the cylindrical resonant cavity as given by the boundary condition that the wave function psi is equal to the z component of the electric field is equal to 0 at rho equal to r, that is when rho is equal to the radius of the cavity, that is at the boundary, and from this the value of capital K subscript mn for the transverse magnetic mode, that is TM mode, is equal to x subscript mn by capital R, where x subscript mn are the nth zero of the Bessel's function j subscript m as a function of x. So the cutoff frequency or the mode frequency, angular frequency for the transverse magnetic mode given by omega subscript m and j superscript Tm is equal to 1 upon under root mu epsilon whole times bracket open within brackets x subscript mn by capital R whole square plus within brackets j times pi by L whole square whole bracket close to the power half. And the lowest permissible resonant frequency in the transverse magnetic mode for the cylindrical resonant cavity is given by omega subscript 0 1 0 superscript Tm is equal to 1 upon under root mu epsilon times x subscript 0 1 upon capital R, and this is equal to 1 upon under root mu epsilon times 2.405 by capital R. And this relation, as we see, is independent of the length of the cylindrical resonant cavity and cannot be tuned by simply changing the length. Cylindrical resonant cavities. Let us look at the case of the transverse electric mode. So again, considering the boundary condition which is given by the partial derivative of the wave function with respect to rho at the boundary of the cylindrical resonant cavity, that is at rho equal to r is equal to 0. And hence, using this boundary condition, the eigenvalues can be found out in terms of the zeros of the derivatives of the Bessel's function. So capital K subscript mn superscript Te is equal to x prime subscript mn by capital R, where x prime subscript mn is the nth zero of the Bessel's function, j prime subscript m as a function of x, and the resonant frequency can be given as omega subscript m and j superscript Te is equal to 1 upon under root mu epsilon whole times bracket open x prime subscript mn by capital R whole square plus within brackets j times pi by L whole square whole bracket close whole to the power half. And the lowest Te mode that is permissible for the cylindrical resonant cavity is then given for m is equal to n is equal to j is equal to 1, with the resonant frequency given as omega subscript 111 superscript Te is equal to 1 upon under root mu epsilon whole times bracket open within brackets 1.841 by capital R whole square plus within brackets pi by L whole square whole bracket close whole to the power half. So if we look at the lowest cutoff frequency for the transverse electric mode, then we see that this frequency does depend upon the length of the cylinder in comparison to the fact that for the transverse magnetic mode, the lowest cutoff frequency was independent of the length of the cylinder. And hence, this frequency can easily be tuned to the desired value by making a length adjustable. So comparing the lowest transverse magnetic mode frequency with the transverse electric mode frequency, we find that the omega subscript 111 superscript Te is less than omega subscript 010 superscript Tm for D greater than 2.03 R. And for such a case, we see that the lowest cutoff Te frequency, that is omega 111 Te, becomes the fundamental mode of the cavity. And this mode is tunable by varying the length of the cylindrical resonant cavity. So students, let us now summarize what all we have learned in this module. So in this module, we have first briefly discussed about the boundary conditions that need to be satisfied at the dielectric perfect conductor interface. Having discussed these boundary conditions, we then went on to explain the use of hollow metallic structures for propagation of the electromagnetic waves in a guided manner, and the production of the resonant waves of suitable frequencies. We then obtained the various modes of propagation of the waveguides, that is the transverse electric mode and the transverse magnetic modes, and we also explained why another mode, the transverse electric magnetic mode, is not possible in the waveguides. After that, we introduced the concept of the cutoff frequencies, below which the propagation in a waveguide is not possible. Next, we made a detailed study of the rectangular waveguides for the two types of modes, that is the transverse electric and the transverse magnetic modes, and obtained the expressions for the cutoff frequencies for both of them. After that, we studied the cavity resonator, which is a waveguide-like structure with the ends closed. And finally, we specifically studied the cylindrical cavity and obtained expressions for the various resonant frequencies for both the transverse electric and the transverse magnetic modes. Then, finally, we also found out the resonant frequencies that are given in terms of the Bessel's functions and the derivatives of the Bessel's functions. We explained how it can easily be tuned to a desirable frequency by making the length of the cylinder variable. Thank you.